guys, and welcome back to the ACE Academy. In this video, we will be looking at the exponential function. Now, in the previous videos, when we spoke about the topic of functions, when I introduced any function to you guys, whether it be the linear, the parabolic, or the hyperbolic function, you know that I first introduced the natural function for that specific type of function. When I say I introduce the natural function for that specific type of function, I'm talking about, let's say for example, the linear function. I introduced you guys to the natural linear function. Then for the parabolic function, I introduced you guys to the natural parabolic function, which had the equation y is equal to x squared. And then for the hyperbolic function, I introduced you guys to the natural hyperbolic function, which had the equation 1 over x. Now in this case, I'm not going to introduce you guys to the natural exponential function. And that is because throughout your mathematics in school, you will not deal with the natural exponential function. This function is a bit tricky, and if you go into perhaps the field of engineering or applied sciences, you will be introduced to it. But until then, do not worry about it, okay? The way I'm going to teach this specific function to you guys is in terms of shape. That's a little shift that I'm going to be doing, right? So we're going to talk about this function in terms of shape because I find that this approach is much easier, okay? So for the exponential function, it usually has the equation y is equal to b to the power x. And this is really different when compared to your previous function, because in this case, you will notice that x is not a base, it is now an exponent. You have some other whole number that is going to be your base. So to understand this function, I'm going to assume that b is equal to 2. So let's say my equation for the function I'm going to plot now is y is equal to 2 to the power x. And let's go ahead and plot this function together, guys. When x is equal to 0, this equation should be y is equal to 2 to the power 0. And as we know, any base, any whole number, when raised to the power of 0, is going to have the value of 1. That is an extremely important point that I want you guys to take note of, because that is the y-intercept of this function. When x is equal to 0, y would always be equal to 1. Because if I had 3 to the power 0 over there, I would get an answer of 1. If I had 100 to the power 0, I would get an answer of 1. So irrespective of the type of base that you're going to get, the y-intercept is going to be 1. Okay? Moving on. 2 to the power 1 should be 2. So I'm going to estimate and I'm going to put it around here. 2 to the power 3 should be 8. So I'm going to estimate and I'm going to put it around here. 2 to the power 4 should be 16. So I'm going to estimate and I'm going to put it around here. Okay? Working backwards. 2 to the power negative 1. That one is tricky. Why is that tricky? Because 2 to the power negative 1 is actually equal to 1 over 2 to the power 1, which is a half. So I'll estimate and I'll put it here. Then 2 to the power negative 2 should be a quarter, so I'll estimate and I'll put it there. And this will continue getting smaller and smaller, but it will never touch the x-axis. And that is very, very, very important, because that tells us that the x-axis is in fact a horizontal asymptote. So when we look at the exponential function, let's just list the points that are important. We have a y-intercept at y is equal to 1 and x is equal to 0, of course. And we're going to have a horizontal asymptote at y is equal to 0, which is your x-axis. And that's how I want you guys to think of this function. Now, drawing this function in, it would look something like this. And that should be the shape of your function. It will continuously get larger and larger upwards in larger increments as your x value goes on because of its exponential nature, and it will continuously get smaller and smaller exponentially going towards the left hand side of the y-axis, because your x values will get smaller and smaller, meaning you'll get fractions, smaller and smaller fractions, but it will never ever approach the x. It will never ever cut the x-axis, rather it will always approach the x-axis. That's an important point I want you guys to take note of, right? When we look at the domain and range of the exponential function, it would have a domain, meaning it would exist for all the values of x along the x-axis. So for domain, we can simply say x is an element of R, or x is an element from negative infinity to positive infinity in rounded brackets, because infinity cannot be contained. Okay. Now when it comes to range for the exponential function, depending on the shape of the function, and I'll expand a bit more on the shape in the next video, depending on the shape of the function, whether this function lies in the negative y region or positive y region, your domain will your range will fluctuate. Now if you're looking at the positive y region, for example, the exponent we have on the screen, exponential function we have on the screen right now, you can see that the range would be from 0 to positive infinity, but 0 is not included. So we can say y is an element of 0 to positive infinity. And both will have round brackets because it's not inclusive, right? Now, another way for you guys to write the range of the exponential function would be y is greater than 0. It's the exact same thing. Now, I know this function is tricky, so I want you guys to hang in there. Just stick with me for a bit, and in the next video, I will explain it in a bit more detail and give you guys some tips and tricks on how to deal with this function. Remember, the only important points for this function is its y-intercept and its horizontal asymptote. And I'll show you guys how we manipulate that as we go on. Until then, guys, all the best, and I will see you in the next one.